Hi, so in this talk, I'm going to look at the symmetries of field theories. Now, I realize that this is, like a fairly broad title for a talk, but I really am going to be talking about what it means for a field theory to have a symmetry in kind of like a broad sense of the meaning. As I start all my talks, let me start this talk with a disclaimer. The first part of this disclaimer is about the content of this talk. I've never tried to give a talk like this before. I'm kind of using Keynote's internal live video things. I'm not actually giving this to an audience. This is a recording. So if this may not work great, if it doesn't, I apologize. But if it comes out reasonable at the end, I'll put it on YouTube. The second part of this disclaimer is so that I'm dyslexic, and therefore there are going to be some words, some phrases that I perhaps get incorrect or I say wrong. If that happens, if something I say is unclear, or you really just have any questions, feel free to ask them. Either send me an email or put them in the comments. The last part of this disclaimer is really about the content or the material of this talk. This is the only graph I've plotted within the last 3 years of my research, and it kind of shows the projects that I have done over my career as an academic. Some of them, those towards the bottom of the graph, are more pheno related. They, like your typical model building projects. Towards the top of the graph, there are these pure mathematics projects, and these are much more involved, much more mathematically rigorous. And fortunately, or perhaps unfortunately for you, or more like unfortunately, perhaps fortunately, the talk that you're going to listen to today is the one in the top right-hand corner of this graph. It's basically a talk on pure mathematics. And when making such a talk, it's often difficult to get a correct balance or a nice balance. So this may or may not work. If it doesn't work, I apologize. If you think of a better way or want me to explain something in a different way, feel free just to put something in a comment or write me an email. The paper this talk is going to be based on is this one here. Oop, pointing in the wrong direction. This one's here. Generalized Symmetries of Topological Field Theories. And there's a paper that I wrote with Ben Gripaios, who was my PhD supervisor, and Oscar Randal-Williams, who is an algebraic topologist at the University of Cambridge. The talk is going to be split into four subtalks. I should say that sometimes there will be text overlapping with my video. I apologize for that. The four subtalks of this talk, the first one is going to be really about motivation, what we did and how it's going to fit in, or how it fits in with the main literature of symmetries. I'm then going to go back to undergrad. We're going to really look at the symmetries of quantum mechanical like theories, starting from, like a fairly bottom-up approach. You don't really need to know much or really any mathematics to understand this beyond that of first year or second year quantum mechanics. And then the first subtalk, we're going to be looking at like generalities, really what it means to be a symmetry of a field theory in a much more general sense. And then the last subtalk, we're going to go on to gauging and these things called Hooft anomalies within this general framework. So let me start with the motivation. I'm going to start right at the beginning, which is perhaps the best place to start. It's way back in 1831, and this person, Michael Faraday, gave a series of lectures at the Royal Society in London. And in these lectures, he showed that electricity and magnetism were one and the same thing, and he did this using the property of induction. In the 2 centuries that followed these lectures, we as physicists have come to know that electromagnetism is due to a symmetry of nature called the gauge symmetry. And gauge symmetries and their global counterparts are already used throughout physics to do a whole host of things, to constrain models, to predict experimental outcomes, etc., etc. Really, they are the bedrock of physics as we know it. So symmetries are very important, and they have been very important in physics for a very long time. Recently, there has been an upsurge in the study of symmetries, really for the sake of studying symmetries. And this is due to this paper on generalized global symmetries, which came out in 2014. And as you can see, this paper has had many citations since then. Towards the end of my PhD, me and my supervisor, Ben Gripaios, we started talking about generalized symmetries. And really, during this conversations, I concluded to myself that I didn't really understand what a generalized symmetry is. I really don't understand a lot of areas of particle physics. And before you stop watching this video saying, okay, he doesn't understand anything, let me explain what I mean when I say understand. When I say I don't understand generalized symmetries, I mean I don't understand it in the sense that I can't go to the ivory towers of the pure mathematicians and explain to them what a generalized symmetry is. And really, this is down to the fact that quantum field theory doesn't have a well-defined notion of a path integral, so it's very difficult to do anything in a rigorous manner in quantum field theory, really because it's built upon the shaky foundation, which is the path integral. So what me, Ben, and Oscar, what we decided to do is we asked ourselves, okay, can we do generalized symmetries in a rigorous manner in a way which may lead to new insights and new understandings, but can also be explained in a mathematically rigorous way in the ivory towers of the pure mathematicians? In other words, can we do generalized symmetries in a rigorous manner? So you're probably thinking to yourself, okay, wait, okay, how possibly can you do generalized symmetries in a rigorous manner if you don't have field theories in a rigorous manner, right? Firstly, you should work out how to do field theories rigorously, and then ask how you do symmetries. So we sat down, we looked on the internet, and we looked for field theories which are themselves defined in a rigorous manner. And the obvious candidate are these topological field theories, which are defined in this area called category theory. There are other candidates of rigorously defined field theories, in particular these geometric field theories of gradient path length that came around in around 2020. So much more recent, much more involved definition of field theories. This is what I'm currently working on. Let me try and get the directions right. This is what I'm currently working on, but the talk is really going to be focusing on these topological field theories. If you don't understand a topological field theory, if you don't know what a topological field theory is, don't worry, you don't need to. For this talk, I'm going to secretly define one for you. Hopefully you won't notice, or hopefully it'll be mathematically easy for those of you who are perhaps not that formally trained in mathematics. Likewise with generalized symmetries, I don't need you to know, the history of or the main content of the physics literature on generalized symmetries. Really, to do this project, I didn't really need to know much of that. So it's unlikely that you are going to have to need to know it to watch this talk. So given what I've said so far, really, we're going to be looking at generalized symmetries of topological field theories. It is unsurprising that the paper, as I've already mentioned, that we're going to be looking at in this talk is called Generalized Symmetries of Topological Field Theories. Perhaps not the most imaginative paper title, but it kind of describes what we're doing. So really, this is what we're going to be talking about within this talk. I want to give you, in the next 2 slides, an overview of the area of mathematics this paper is written in. The reason I'm doing this is that the rest of the talk is going to be, like fairly hand wavy, fairly ad hoc. And the reason I'm doing this is so we don't have to go into the mathematics, but I really want to give you what the area of mathematics is so you understand, or at least, can reference it, or if you hear this area of mathematics referred to before, you can go, oh, okay, it's been used to teach generalized symmetries, etc., etc. So that area happens to be this area called toposphere, and I put this math overflow post on to kind of signify the significance of higher toposphere to the mathematicians. The book that this math overflow post is talking about is this book called Higher Toposphere by Jacob Leary. And really, it's a massive book, but it really is kind of like revolutionary to mathematics in the sense that it gives an overarching framework of how to do lots of things in mathematics. And it's really nice. The area of toposphere is related to higher category theory. As this diagram shows, it's related to this thing called algebraic topology. You can relate it to type theory, and really it encompasses a lot of mathematics. And I think, let me step onto my soapbox here, I really do think that physics one day will be written in this sort of language, just because how important it is to mathematics. And I think physicists tend to have this idea that we can draw the line in the sand beyond group theory and not cross it and say, okay, fine, whatever, we don't have to understand anything beyond that. But really, I think that we should be open to learning new areas of mathematics, and I think higher toposphere is perhaps one that will be important to physicists in the future. So this kind of ends the motivation. Let me give you the 3 takeaway points from this section. The first one is that generalized symmetries are important to physics. You know, that paper that I showed you from 2014 has so many citations. It's like 800 citations plus. What we're going to try and do is we're going to try and do generalized symmetries in a formal manner. And then I'm going to, or then the underlying mathematics of this area really is topos-theory, although for the rest of this talk, we're not really going to go much into the nitty-gritty details of topos-theory. In an apparent way, I will secretly do it, but that's okay. Great. So let me take a glass of water, and then we will go on to the example, or an example. So what am I about to do? I'm going to choose a field theory. Fair enough. I'm then going to work out its symmetries. I'm then going to present a classification of symmetries. So what we're going to be doing is really what we kind of did in the paper. We're going to take a field theory, we're going to find its symmetries, and we're going to, present a classification. Okay, and this is really going to give you an idea of the sorts of techniques or the sorts of like the bedrock ideas for which we can define generalized symmetries in a rigorous manner or symmetries in a rigorous manner used in this area of topos theory. So to start off with, we're going to play a game, and this game is going to be called Find or Name the Simplest Field Theory. Because if we can't do generalized symmetries in a rigorous manner for the simplest possible field theory, then we're not going to be able to do it for anything else. So let's try and think of the simplest field theory that we can. So the dimension of the simplest field theory is going to be, of course, 0 plus 1 dimensional, right? What else could it be? Anything else is going to be more complicated than the 0 plus 1 dimensional field theory. And given it's 0 plus 1 dimensional, we're therefore working within the realm of quantum mechanics. The next thing you need to define a quantum mechanical theory is a Hamiltonian. Let me take that Hamiltonian to be the zero Hamiltonian because, why not? It's the simplest theory possible. Let's take the zero Hamiltonian. Nothing happens. It's a very boring theory. Your states kind of stay in the same state. No weird time evolution happens for anything like that. The state space, so this is like the vector space which underlies the Hilbert space. We're going to take that to be an n-dimensional vector space where n is finite. So this is a simplification. N could be infinity in general or infinite in general. This vector space need not have countable number of elements. But for us, we're going to take it to be a finite dimensional vector space where n is an integer number. There's one more bit of data you need to define a quantum mechanical field theory, and that's an inner product. For the purposes of this talk, I'm going to assume there isn't an inner product. This gives us something called Euclidean quantum mechanics rather than traditional unitary quantum mechanics. And Euclidean quantum mechanics, you can just think of it. You can do basically everything you can do in unitary quantum mechanics except Born's rule, so you can't find probabilities or anything. But, what I'm going to tell you easily generalizes to unitary quantum mechanics. So the important thing to note is that such a theory is determined by the integer n, and really that's it. If you give me the integer n, the natural number n, I should say, it has to be, of course, positive or 0, then you can really, that really defines the field theory. So the question that we asked ourselves is, what are the G symmetries of this field theory where G is a group, right? If you give me a group G, can I find every possible G symmetry of this field theory? Whenever you ask a question in physics, you should always ask yourself, why can I even ask this question, right? That may seem like a trivial thing, okay, like why, of course I can ask this question, doesn't make sense. But really what I mean here, does it make sense to ask this question? Does this question actually have an answer? So why can we even ask this question? Why can we even ask the question of whether a field theory, whether we can write down all of its G symmetries? And the reason we can ask this question is that a classification exists. A classification of G symmetries of a field theory exists. And this is a non-trivial statement, right? You can show this using the mathematics, you can show this using topos theory, but really it's a non-trivial statement, right? There didn't have to be a classification. It didn't have to be like this, but it turns out that it is. So given that a classification exists, we can then go and ask, what are the G symmetries of this field theory? So let me call the vector space underlying this field theory, let me call that Vn. And really this is the only bit of data that we have. Remember, our field theory is really labeled by n, and that really labels the dimension of the vector space. But if you give me a vector space, you get for free a bunch of linear maps that take that vector space to itself. Let me draw these like this, and I'm going to assume these linear maps are invertible. So these are basically n by n matrices that act on your vector space, and they're invertible. They're invertible because we want a group action to be invertible. So really, this really is the only structure that we have to play. This is whatever we define a symmetry with. It really has to be based on this structure. So a guess of a G symmetry is a homomorphism from G to GLN. This is like the naive thing that you may assume is a G symmetry on one of these field theories. But we can ask what this would correspond to in the physicist parlor, in the physicist language. And a homomorphism from G to GLN corresponds to a representation. It corresponds to a representation on your vector space Vn. But we know from physics that you don't just have representations. Indeed, this guess has to be wrong because you have things like projective representations. And we know that you have projective representations in physics and that they give you well-defined symmetries. So this is wrong. So at this point, I went to the maths department and I asked them, how do I define a symmetry? This is a real fake transcript of a conversation I had with a fake mathematician about how to define a G-symmetry. And I asked them, how do I define a G-symmetry? And they said to me, well, a G-symmetry is a G structure on a set in X. I don't know what set is. I haven't told you what X is. Okay, but let's take this. It seems a fairly good notion of a G-symmetry. It's some sort of structure on a element of some object. And then they said the first thing you have to do is you have to find a G action on X. Okay, seems like I can do that. I don't know what X is, but I could probably guess what a G action on it is. They then said you have to find the fixed point structure on Z in X, if it exists. So at this point, I went back to my office and I wrote down a little worksheet that I said to myself that I should fill out. And in the top left-hand corner of this worksheet, we have to first specify what X is. And really, this is going to tell us, ultimately, what a G-symmetry on a field theory is. So I scratched my head, and I asked myself, what could X possibly be? Well, there's only one thing that X could be, and that is this sort of structure that I gave you earlier. And this structure is something called a groupoid in category theory, and it really is the underlying structure of our theory. The next thing we want to do is we want to find a G action on X, and the only thing that we can do here is we can map or we can move these matrices around. Really, that's the only thing, the only freedom that we have. We can't move the vector space around because there's only one vector space. So for every G, little g, in the group G, what we can do is we can move these matrices around, and that's the only thing that a G action can be. We want to do this in a way which is consistent with, multiplication of matrices and inversion of matrices. In other words, this map F has to be a homomorphism from G to the automorphisms of GLN. To the mathematician, this notion is something called a two-functor, and you really do get this for free. I'm presenting it in perhaps an ad hoc manner, but you really do get this for free. We can then ask what are the fixed points of this action. After some hand waving, or not hand waving, but some abstract nonsense, you get that the fixed points are a map of sets from G to GLN, such that this kind of like twisted multiplication rule is satisfied. Okay, so this is really what we mean by a G symmetry on a field theory. It's really this end result in free, this set of data that satisfies this condition. It's what we mean by a G symmetry given the action in step number 2. So we had better make sure that this corresponds to what the physicist, expects. So let's first make sure we can get back representations, because we know that physicists expect representations on accident quantum mechanics, and that would be a good notion of a symmetry. So let's take the G action which acts trivially on every element of N. So basically f of g, this map, this homomorphism, G goes to the automorphisms of GLN. Let's assume that every little g gets mapped to the identity automorphism. In other words, this g action does nothing. Nothing happens. In that case, the fixed point structure, basically from the third point on the previous slide, basically becomes this equation up here. And obviously, if you know anything about representation theory, this corresponds to a representation, an n-dimensional representation of the group G. So remember our naive guess from the previous, a couple of slides ago. The reason we threw that guess away was that we got representations, but we didn't get projective representations. So if this guess, this notion of a symmetry is correct, we had better make sure that we get projective representations back. So let me show you how you get projective representations. In this case, I want my action to act via inner automorphism. So for each little g in G, we're going to act via this conjugation with respect to a matrix UG in GLN. So this is going to be really our group action, and it's going to be defined by this, F is going to factor through the inner automorphisms of GLN. The fixed point structure then becomes what I've shown in the step 3 above. It's really a map of sets such that this equation holds with these UGs and UG minus 1s. And if you do some rearranging, you can rewrite this with this epsilon G1, G2 term. And this epsilon G1, G2 can be shown to satisfy the co-cycle conditions, and therefore this defines a projective representation. So I've shown you that we have a good definition of a G action in the fact that we get representations and we get projective representations. But this is a classification. So we can ask the question, what else? We can ask the question, what is every single possibility of a G action on this quantum mechanical theory? Well, to understand this, let me give you the automorphisms of GLN. So the automorphisms of GLN are these things here, and they basically determine the allowed actions, or they give you like an idea of the allowed actions of G on GLN. Of G on this group weight structure. So the first automorphism is the identity. The second one is an inner automorphism. The third one is some sort of conjugation, or really like a field automorphism. The third, let me count. The fourth one is like inverse transposing, and the last one, you take your matrix and you times it by the determinant of M. I can tell you the fixed point structure. So the first one, you get back representations as we shown. The second one, you get back projective representations. You then get semi-linear representations for this field automorphism sort of thing. These last two, they don't have names, but you can easily write down the equation that those sorts of representations satisfy. Given this is a physics talk, let me tell you the physics behind of these. Hopefully the physics behind representations is somewhat obvious. These inner automorphisms are related to, for example, the rotation of an electron. This semi-linear representations are related to time reversal. M goes to n-1t. You can think of it somehow related to orientation. Not quite orientation shifts, but if you include or disinclude an orientation on your space-time. And this M goes to the determinant of M. I don't really know where this comes into physics, but if anyone does, please do let me know, because I'd be interested to know if anyone has ever used a symmetry in quantum mechanics where this is of relevance. So the three takeaway points from this part of the talk is that symmetries can be classified. All of this can be done naturally, like I presented it in a fairly ad hoc way, but all of this can be done in a way which is natural in a sense that it flows out from the mathematics in an easy way, and that for quantum mechanics you get things like representations, projective representations, and a bunch of other things. So as I get a bit of water, let me show this slide, which is just a bit of fun. I asked this AI to generate a teddy bear version of a bunch of scientists, and maybe you can have a guess of which scientists are which. Okay, so let me go on to the third subtalk, and I'm really going to be talking about generalizations. So the first thing I'm going to do is I'm going to talk about this thing called the homotopy hypothesis. Sounds complicated. Hopefully I'll present it in a way which is, fairly understandable to a physicist. And I'm going to redo the calculation we did in the second subtalk, but using topology. Lastly, I'll generalize to higher form symmetries. So I'll basically take everything that we've done and I'll generalize what we did to higher form symmetries. And hopefully this will, bring everything together and make what I've kind of said in the previous parts of the talk worthwhile. So to understand this part of the talk, you need to know the very basics of topology. And really, let me give a pseudo definition of a topological space. This is nowhere near rigorous, and it's, of course, wrong naively, but it gives you an idea of what a topological space is. A topological space is like a manifold, but it's got no smooth structure. So don't talk about like dimensions of topological spaces or like coordinate systems on topological spaces or differentials, etc. None of those make sense in this context, in the context of topology. Here's some examples of topological spaces. As you can see, this cross obviously doesn't have a well-defined notion of a dimension, and so on and so forth. The second thing I need you to know is about homotopy groups. Pi0 of topological space is really just the number of disconnected components. Pi1 of x is the number of loops up to homotopy. This star means I've chosen a point in x to start the loops and end the loops. Pi2 of x is kind of like higher form loops, higher types of loops, etc. So Pi1 of S1, for an example, is said. Pi n of Sn is also said. This is something called stable homotopy theory, and it kind of shows, probably gives you an idea of what these sorts of things are like. So, I mean, take the S1 example. You have S1 loops. Sorry, you have said worth of loops in S1, which can't be smoothly deformed into one another, and that's where the set comes from. So if we want to generalize what I did in the previous subtalk, if we want to generalize that from this very simple example of a 1D topological field theory, this 1D field theory where the Hamiltonian was zero, we would have to take the structure called the groupoid, and we would have to go to these things called infinity groupoids. And infinity groupoids are like groupoids, except they have not just arrows, but they have arrows between the arrows, and they have arrows between the arrows, between the arrows, and so on and so forth. And these arrows have to satisfy certain coherent conditions. An amazing theorem in topos theory or category theory, higher category theory, is that infinity groupoids are the same thing as topological spaces. You can, instead of working with these things called infinity groupoids, you can work with these things called topological spaces. And although infinity groupoids are difficult, these topological spaces are easy. So we're going to really replace this notion that I've been calling the groupoid, or this point with these arrows between them. We're going to replace that with a topological space. And I'm going to call that space X, and this is going to be how roughly we're going to interpret it. So a point in X is really a field theory, and the paths in X are really different ways to go between different field theories. So a loop starting and finishing at a given point are really different, like automorphisms or different ways you can take a field theory back to itself, up to homotopy. And then, so these loops would be arrows, and then if you consider homotopies between homotopies, they would be like arrows between arrows, and homotopies between homotopies between homotopies would be arrows between arrows between arrows, etc., etc., etc. This X really for a lot of what I'm going to be talking about is really going to be the space of topological field theories, and you should think of it not as containing one field theory, but containing many field theories where their equivalence is determined about whether they're in the same connected component or not. So let's redo the calculation that we had in the previous subtalk. So in subtalk 2, the first thing we need to do is we need to specify what is X. So remember, X in our previous case was this object, this Vn, with these bunches of these maps, these matrices, these general linear matrices between them. In our case, X is going to be replaced by a topological group, a topological space, and that topological space is going to be BGLN, and this is defined by the fact that it has a first homotopy group equal to GLN. And this tells you that there are GLN worth of different arrows, and this is kind of how you see that it corresponds to what we had before, right? It's got one point up to homotopy, and GLN worth of arrows, or GLN worth of maps up to homotopy. In other words, this gives you back the group width that we had before. So what is a G action on X? Very roughly, a G action on X, on topological space, is kind of what you'd expect. It takes points in X to different points, and it makes sure that you can do it in a way which is like you can do one G action followed by another, and that would be the same as if you do them both at the same time. This is a simplification. There are actually much more general types of G actions that you have to consider. This is one type of G action. Good. So the fixed points of these actions are something called homotopy fixed points. I'm not going to go into the definition of these. There are slightly more general type of fixed points. So for example, a G action could be, take the action of SO2 on a plane, or the rotations of a plane. That would be an example of a G on a manifold, which is like a topological space. Do rotations on a plane. The fixed points of that would be the origin, because it doesn't move. Homotopy fixed points are like this, but they contain slightly more generic structures. So let me go back to the examples we had in the previous subtalk. The first example you get by taking the trivial action on X, and that's going to give you back representations. And the second example is you take non-trivial actions on X, and that's going to give you back these twisted sorts of representations. These more general things like semi-linear or projective representations. So I promised you at the start of this talk, I promised you great things. I promised you that we were going to do topological field theories, and we we're going to do generalized symmetries of topological field theories. But so far, I've kind of perhaps been a disappointment that I've only considered ordinary symmetries of 1D topological field theories, and that was quantum mechanics. So really, I haven't really told you anything exciting or new about generalized symmetries. But the important thing, or the nice thing about what I've told you is that it's very easy to take what I've told you already and to generalize that to topological field theories of any dimension and to generalized symmetries. So if you want to work with high dimensional topological field theories, all you have to do is replace this X with the space of d-dimensional TFTs. That's it. Just replace the topological space with a different topological space corresponding to the space of d-dimensional topological field theories, and that's guaranteed to exist. Given that we're working in topology, we can take our group G not to be a discrete group, which is what I've implicitly assumed throughout this talk, but we can take G to be a topological group. Really, we're working in topology, so why not? We can take G to be a topological group. And if you do that, you get back higher form symmetries. That's it. You just replace a discrete group with a topological group, and you get higher form symmetries. This is really the beauty of this construction, and everything else follows in exactly the same way. There's nothing you have to do special for generalized symmetries. You find that you act with a group action on X, the same thing that I showed on the previous slide. You find homotopy fixed points, and they will be higher form symmetries, generalized symmetries acting on your field theories. So doing this all with like geometric field theories is a work in progress. We're taking gradient path lofts definition that I talked about earlier in this talk. We're trying to use that to do this whole construction in topological field theories and hopefully in geometric field theories, and hopefully this will be out fairly soon. So let me give you an aside. To the physicists, we often talk about these higher form symmetries and the fact that they're abelian, and it's very easy from our construction to see why this is true. These pi 0 of G, pi 1 of G, they can be thought of as the like the one form or the two form component of your group action or of your group, and how that acts on your X or on your topological space. And the higher homotopy groups of a topological group happen to be abelian, and in this sense, this is how we can easily see that higher form symmetries are abelian. So what are the three takeaway points from this part of the talk? So the first thing is that the homotopy hypothesis means that we can work with topological spaces. The second point is that we can study any dimension of topological field theory just by replacing X with the space of like d-dimensional topological field theories. And the last thing is that generalized symmetries are natural, right? You just replace the discrete group with a topological group, and then everything else follows in exactly the same way. So let me go on to the last part of this subtalk, which is on gauging. So I suspect that you're all thinking, what about gauge theories? Let me tell you, I've only talked about global symmetries. Tell me about gauge symmetries. Gauge symmetries are very important to physics. So let me talk about gauge theories. What am I going to do? So the first thing I'm going to do is I'm going to ask if we gauge or we globalize. It's a question. We can ask it. We're then going to suggest or see where Hooft anomalies come from, and then I'm going to very briefly mention this thing called the cobordism hypothesis. So let me consider two topological spaces which represent two different spaces of field theories. So G of X is going to represent T of T's with a G gauge symmetry, and this X of HG is going to represent T of T's with a global G symmetry, and that corresponds to the homotopy fixed points of a given G action on your space. So when we gauge, or when we go from a gauge theory to global symmetry, or global symmetry to gauge symmetry, we follow either one of these maps, and one of these maps may not exist. So really, this is a question that I want to ask, right? Do we take a gauge theory? Do we have a map that takes a gauge theory and turns it into a global symmetry, gauge symmetry, and turns it into global symmetry? Or do we have a map which is a gauging map that takes a global symmetry and turns it into a gauge symmetry? It should be easy to understand that the gauging map just doesn't exist. And the reason this doesn't exist is that we have things like Hooft anomalies, and there are not unique ways to gauge a theory. So that can't be a map. There can't be a map which gauges, otherwise you could gauge every possible G symmetry. In other words, we must have this globalization map. You can always take a gauge symmetry and globalize it, consider its global counterpart, but you can't always take a global symmetry and consider it its gauge theory. This kind of tells us that we must have a map called a globalization, which goes from G of X to X of HG. So what is gauging in this context? Really, gauging is about taking a point in X of HG, this space of topological field theories with a global G symmetry, and asking what points map down to it under this globalization map, and trying to work out if any points exist, or how many points exist, or do they exist. So really, we can see Hooft anomalies as properties of this globalization map. If this globalization map is not surjective, or really what I mean here is something called essentially surjective, kind of represented by this diagram, this bottom point, there's no map in the left-hand side, there's no point in the left-hand side that maps down to it, then we say we have the Hooft anomaly. There's no way to gauge that symmetry, to gauge that global symmetry. Those of you who know this diagram is wrong, technically, but I won't go into details of why. If this globalization map is non-injective, like a situation that we kind of had before, where you have a point on the global, or point with a global symmetry that has two different possible inequivalent ways of gauging, then we say you have this thing called a Hooft ambiguity, and this is a terminology that we came up with. If you have an X of HG, there actually need not be a G of X with a globalization map into it, and if this happens, we say there's a metaphysical Hooft anomaly. And this occurs for something like a projective representation, a non-trivial projective representation, and this corresponds to the statement that non-trivial projective representations can't be gauged. And the last thing that can happen is that there may be two different globalization maps into the same X of HG. This is slightly more difficult to study because you have to put some notion of equivalence on globalization maps, but it may exist. So let me finish really with the most important theory in topological field theories, and this is the cobordism hypothesis. It kind of debated whether it's been proved or not, but this says that this globalization map is an equivalence if you're working with fully local field theories. So if you're working with field theories that are defined on every codimensional manifold, then this globalization map is an equivalence. In other words, to the physicist, this means that there are no Hooft anomalies or ambiguities for fully extended theories. So let me finish here. Let me give the 3 takeaway points. We globalize, or the 3 takeaway points of this last subtalk. We globalize, but we don't gauge. Hooft anomalies result from the properties of this globalization map, and the cobordism hypothesis is powerful, and it relates locality to Hooft anomalies and gauging. So with that, let me finish this talk here, and let me stop recording.